Hi, Dr. Tashawn here, and in this video we're going to look at the definition of continuity at a point of a function. Before we take a look at the words of the definition, please look at the graph over here. This graph is a function, and as you look at the graph left to right, you see that there's a lot of points of discontinuity, a lot of jumps in the graph, holes in the graph. So we're going to use this with the four examples in a moment after we look at the definition to really investigate what the definition of continuity at a point is. So take a look at the screen. Let's look at the definition of continuity on the screen. So in order to have continuity at a point, there are three conditions in the mathematical definition that must be met. The first condition that must be met is the function value at that point. The function value must be defined. The second condition, the limit must exist. And then the third part of the definition, that function value and that limit must equal each other. So this is what the definition says. We're going to go through this definition in a graphic representation. We're going to look at graphs and pictures of this definition. I'll come back in another video to do some algebraic representation, working it out. So we've got some graphs here on the board. We have A, B, C, and D. Let's look at four graphs here on the board. Each of these four graphs, you have discontinuity in each of these four graphs. So continuity, just as you would probably think, you trace it on a curve, trace from left to right with your pencil tip. If you can trace your pencil tip from just left to right and not pick that pencil tip up, then you have continuous function. So if you got to trace and then pick up your pencil and put it back down, discontinuous function, just as the name implies. It's just, continuous. It just keeps going. You don't have any gaps, jumps in the graph, anything like that going on, any holes in the graph. So, but we have to use mathematical definition, this mathematical definition to explain things when you're doing things in standardized form. So let's look at letter A. We want to know why letter A is not continuous at point C. In order to negate the continuity, in order to explain why function is not continuous at a point, you have to explain one of the conditions that's not met. Okay, so if all three conditions are met, you have continuity. If a function is discontinuous, it's because one of the conditions isn't met. So let's see which one's not met. So letter A, well, condition one says the function value must be defined. Do we have a function value for letter A? We do. It's right there. It's the closed circle. Okay, so closed circle means there's defined values. Open circles where they're not defined, but closed circles. So yes, condition one is met because we have closed circle right here. Condition two, does the limit exist? Okay, so does the limit exist? Well, the limit is, when you're taking the limit of a function, you're not looking at the C value, you're looking at what happens as you approach from the left and the right, okay? So, and I have another video out of this, but as you approach from the left and the right. So limits, for a limit to exist, if you're approaching a value from the left and from the right and you're going in the same place, you have a limit. For a limit to not exist, well, when you're approaching the value from the left and the right, if you're not going in the same place, limit does not exist, okay? Function values tell you what is happening at the point. Limits tell you what's happening as you come in from the left and the right, okay? So we have the function value, condition one is met. Do we have a limit? As you approach from the left and the right, you see they're not going the same place. The limit's not existing here, okay? So is this a continuous function? No, it's not. Why is it not a continuous function? Because the limit, condition two, is not met. The limit does not exist, okay? Let's look at letter B. Letter B, let's see why letter B, the continuity is destroyed. So we're going to first take a look at, do we have a function value that's defined? Well, when you're looking at this, you trace from left to right, there's an open circle, but there's no closed circle at all. No closed circle, we have no defined value. When X is C, we have no defined value. So because of that, not continuous, and it's because condition one is not met, you don't have a defined function value, okay? Let's take a look at letter C. Letter C, do we have continuity? Well, is the function value defined? For letter C, yes, the function value is defined. It's right here, okay, the closed circle. Do we have a limit? Does a limit exist for letter C? Well, does a limit exist? So if you look coming from the left and coming from the right on the curve, both sides are going the same place, okay? So you have a function value down here. It's defined. And you have a limit up here, it exists, okay? So we've got condition 1, condition 2, but what about condition 3? Condition 3 says that the function value down here and the limit up here must be equal, and that's not the case. So letter C, you have discontinuity because the function value and the limit are not the same number, okay? So that's why continuity is destroyed here. And finally, letter D, do we have a function value? Do we have a defined function value? Yep, here is the closed circle. Do we have a limit? Well, the limit from the left, the limit from the right, when you take the one-sided limits, they're not going the same place. Limit does not exist. So letter D, continuity is destroyed because condition 2 is not met. All right. So there's a little bit to get started here. Let's take a look at our example over here on the board. Same idea, but I put some numbers to it, so you might be able to see it pretty well with numbers. Okay, so let's see how this is going to go. We're going to do these 4 examples based on this diagram on the board. So let's go ahead and start with example number 1. Example number 1, all right, we're going to pick points. We're going to use -1 for example number 1. We're going to use x equals 1 for example 2. We'll use x is 2 for example 3, x is -2 for example number 4. And we're going to investigate continuity at each of these points. So example number 1, let's start with f of -1. So we want to go to -1, and so what is the function value at -1? Let's actually write the number down and represent what it is. So do you remember from algebra class, how do function values work? Okay, so you know this notation, right? Okay, y equals f of x. This is your function notation, right? So y equals f of x. When you're evaluating a function, the number in the parentheses they're telling you is the x, okay? So, and then what do you have to do? You have to, in turn, you give them the y. All right, so anytime you're evaluating a function, evaluate the function, they tell you the x, your job is to tell them y. What does this mean? When x is -1, what is y on our graph? So let's come over to our graph, go to the x-axis. When x is -1, what is the y-coordinate? Because the closed circle is sitting right on the x-axis, the y-coordinate would be 0, so 0 for this value. All right, f of -1 is 0. Let's take a look at the limit. What's the limit as x approaches -1? Okay, so now we're going to take the limit from the left, limit from the right. As you come in from the left and the right, where are the y's going? The y's are going to 0. They're also going to 0. Okay. All right. So remember how this works. Function values, we want to know what's happening at that number. Okay. They tell you the x, you tell them the y at that number. Okay. But limits, you never have to get to that number. It's about what's happening as you approach from the left and the right. With limits, if you're going the same place, you have a limit. All right, with limits left and right, if you're not going the same place, then it does not exist. Do we have continuity at x equals -1? Let's see. We've got to make sure the conditions in the definition are met. Condition number 1. Condition number 1 is the function value defined. Yes, it is. It's 0. Condition 2, does the limit exist? Yes, it does. It's 0. Condition 3, does the limit equal the function value? It does. Okay. Do we have continuity? Yes, we do. Why do we have continuity? I'm just going to write because all conditions are met in definition. Just write it like that for now. Okay. Let's look at example number 2. What is f of 1? When x is 1, what is y? When x is 1, they're telling you the x, what is y? You got to go to the closed circle. When x is 1, y is 1. So f of 1 is 1. Okay? All right? What is the limit as x approaches 1 of the function? As the x's approach 1. Okay, now be careful here, because as you come in from the left, the y's are going to 2. As you come in from the right, the y's are going to 1. Okay, what about this limit? You see the left and the right are not going the same place, so we say that the limit does not exist. In order for a limit to exist, the left and the right have to go the same place. Do we have continuity? Check our definition. Are the 3 conditions met? Okay, condition number 1 says that the function value must be defined. It is, it's 1. Condition 2 says the limit must exist. The limit does not exist. So do we have continuity at x equals 1? We don't have continuity. Why don't we have continuity? Because the limit does not exist. I'll just put D and E for short. Because condition 2 is not met. All right. Let's take example 3. What is f of 2? Remember from algebra class, what is f of 2? When x is 2, what is y? So let's go to 2 on the graph. When x is 2, ooh, there's no closed circle, okay? So what about when x is 2, what is y? We don't have a closed circle there. It's not defined. This is not defined. We have open circle, but no defined closed-in circle. Do we have a limit? The limit as x approaches 2. So not looking at what's happening with limits, right? Just to the left and just to the right. As you approach 2 from the left and the right, are the y's going the same place? They are. They're actually going to 2 on the y-axis. We do have a limit, all right? So we don't have a defined value at x equals 2, but we do have a limit. Do we have continuity? In order to have continuity, the 3 conditions in the definition need to be met. Condition number 1, do we have a defined function value? We don't. Okay, so do we have continuity? No, continuity is destroyed because condition 1 is not met. Okay, so we don't have continuity because condition 1 is not met, and so that's because the function value, because f of 2 is not defined. And then finally, let's look at example number 4. Example number 4, what is f of negative 2? In other words, when x is negative 2, what is y? When x is negative 2, what is y? All the way up to the closed-in circle, it looks like y is 3 there. Remember, they give you the x, you're telling them the y. All right? What is f of negative 2? I'm sorry, what is the limit as x approaches negative 2? Okay, so the limit, now negative 2, as you approach from the left and the right, where does it appear that the y's are going? Okay, appears the y's are going to 1, all right? So when x equals negative 2, y is 3. That's what's happening at negative 2. But as you approach negative 2 from the left and the right, the y's are going to 1. Do we have continuity? Well, we've got to check, are the 3 conditions of the definition met? All right, do we have continuity? In order to have continuity, the function value must be defined. It is, it's 3. The limit must exist. It does, it's 1, okay? What about that third condition though? The limit must equal the function value. Oh, we don't have condition 3 here, so do we have continuity? We don't have continuity. And why don't we have continuity? Because the limit as x approaches negative 2 of our function is not equal to the function value at negative 2. This is why we don't have continuity. What was that limit value? It was 1. What was that function value? It's 3. So condition 3 says these two must be equal. They're not equal, so condition 3 is not met. Okay? So hopefully this example with numbers helps you, okay? Try to get you to negate each of the conditions once. So example 1, continuous function, okay? In example 2, this is discontinuous and continuity is destroyed because condition 2 is not met on the definition. All right, example 3, discontinuous function because condition 1 was not met. All right, example 4, discontinuous because condition 3 was not met. So here's an example that encompasses all parts of the definition. All right, so hopefully this graphic representation of seeing your definition of continuity will help you with your studies, the study and the continuity concepts. So I'll come back and do some algebraic stuff in another continuity video. But for now, I hope this helps. Thank you for watching, and I appreciate it. Bye-bye.